Just start out with some examples. There's no real theory here, it's just a matter of doing it. Okay, now things are a little more complex. And English can help in some cases, but not in many. So we have to use this process. Now that's called a conditional equation. That's the kind of thing that comes out of a word problem. We don't deal with those. We go through a series of steps until we get to what's called isolated, which means x equal to something, and the something will be the answer. So we change the equation. Our whole process is changing the equation. There's another process that could be used to solve equations, but it would be ridiculous. And that is, well, just start substituting in some numbers for x and see if it works. You know? And, if you're a good guesser, that's okay, but there's an infinite number of numbers, so you may get old and gray by the time you find it. So we go to the isolated, and that's what we're after here, isolating that x. Okay. Now here's the best way to do it. There's several ways to do this, but the best way is, first of all, isolate the term that has the x in it. There are two terms here. Terms are things that are added or subtracted. Here's term 1, here's term 2. Right. We want to isolate that term right there. We want to get it by itself. And then we'll be able to deal with the multiplication process and so forth. So first of all, we'll get rid of the 3. Well, how do you get rid of a minus 3? You add 3. That adds up to nothing. But you have to add 3 to that side too. Okay, this goes to 0. Here's a 2x equals 18, because you have to add 3 to both sides, huh? All right, now the problem is the x is not known yet because of the multiplication by 2. But you undo that with division by 2, and it's pretty simple. Okay, 2 into 2 is 1. There's your 1x, but we never write the 1. 2 into 18 is 9. So there's the answer right there. X is equal to 9. You can put it back in, make sure. 2 times 9 is 18, take away 3, yep, that's 15. So it works. Let's do a few of these so we get used to it. Okay, 14 is equal to y over 4 plus 8. Once again, isolate the term that's got the y in it. Get rid of everything else, in other words. All right, to do that, I'd have to subtract 8. Well, if I'm going to do it from that side, I must do it from this side also. Do it horizontally, do it vertically, it doesn't make any difference. There it goes. Now you've got y over 4 by itself, and here you've got 6. And undoing that division is a matter of multiplying. That's the opposite operation to division, so multiply by 4.
Where did that 14 come
Multiply
from?
by 4 here. Sorry?
You got 14 up there.
14. Yes, I do.
Where did it come from?
It actually came from the book. The original equation was 14 is equal to y over 4 plus 8. Then I subtracted 8 from both sides, and that turned into a 6. 14 minus
No,
8.
because I didn't see the 14 up there when you put 8 equals y over 4.
Here's the original. The original is 14 is equal to y over 4 plus 8. Okay? So what I'm doing is trying to isolate this thing here. And I subtract 8 from this side to get rid of that 8. But I have to subtract 8 from this side also. And that gives me the 6. Now down here, the reason I got the 4 is because I want to get rid of this division by 4. So I multiply by 4. And I have to multiply by 4 over here also. So I'm doing the same thing to both sides, in other words. So I get a 24 here and a y here, because that cancels out. When things are multiplied, they cancel. And that's it. And 24 is the solution to that original equation up there. 24 divided by 4 is?
Say that again?
6 plus 8.
Oh my God.
It does work. So the real world gives you these conditional equations. Now, what are they? It's important to understand this. Tomorrow we're going to be going into the applications. What we're going to do is take a real world situation, a time-space situation, and make it into math. We're going to actually mathematically model the real world and solve the math equation. And you say, well, does you go outside and measure things, and would you get the same answer? And the answer is yes, you would. So what we're doing is modeling everything that goes on in time and space and creating equations like algebra equations and so forth, and dealing with the world on our pieces of paper. It's kind of a strange phenomenon. And this is what shocked people when they first developed this stuff, because they actually realized that they could use their minds to model this world, and it worked. It's just an amazing thing, you know. It says something, but that's philosophy, and that's not this course. I won't give the hint as to what it says. I'll let you contemplate it. All right. 2 times z minus 9.2 equals 2.6. Yes, we can have decimal numbers in equations. In fact, most often you do. Nothing changes here. The philosophy toward this is exactly the same. We want to isolate that z term first. So we have to add 9.2 to this side so that the 9.2 disappears, but then we have to add it to that side too. Out it goes. Here's 2 z's. Over here, we just simply add, that's an 8 and 11.8. Okay, now the problem is the multiplication by 2, so we undo it, we divide by it. And z turns out to be 5.5 and 0.4, 5.9. Okay, now I want to go back here to this one to show you that it is not the only way you can work. But it will also show you that you probably don't want to do the other way. All right, let's suppose instead of adding 3 to both sides like we did before, so we could get the 2x by itself, let's suppose we divide it by 2 first. I mean, there's some justification for that. You know, you want to get rid of that multiplication by 2, so let's divide both sides by 2 and see what happens. Okay, now you have to divide the entire left side by 2 and the entire right side by 2. You want to keep the scales in balance. Huh? What does this mean? This means both of these terms get divided by 2. So this becomes 2x over 2. This becomes 3 over 2. And this becomes 15 halves. Well, we didn't have fractions a moment ago, now we do. It's okay, it can still be done, but you gotta love fractions. And let me see all the fraction lovers in here. Right. Lewis loves everybody, that doesn't count. All right, so. All right, the point here is, yes, you can do it another way. 2 into 2 is 1, there's the x. Okay, minus 3 halves equals 15 halves. Okay, now we want to get rid of that subtraction of 3 halves. Well, we'll just add 3 halves, that's all. And likewise over here. This goes to nothing. Now we've isolated the x. And now we have 15 halves and 3 more halves. That gives us 18 halves, which is 9, which is the solution we got a moment ago. This is considered more complicated. And you know, if you have situations where you have different size fractions already, and then you put some more fractions in there, it can get very complicated. So as a result, people don't do it this way. You don't do the division first, you do the subtraction first. Get that term by itself, then do the division. That's the way that's recommended. Even books recommend that. All right, I erased it again, didn't I, Lewis?
No,
I got a habit of doing that. All right, so now let's do something we haven't done before. 4x plus 5 is equal to minus 2x minus 13. What's the difference here? We've got x's on both sides. That's never happened before.
Yeah.
And remember, x is an unknown, but it does stand for a number. I mean, we've been getting numbers for x all along here, so It's a number, it's just, we don't know it yet. So therefore, 4x is a number, and 2x is also a number. Okay? Our whole goal, keep in mind the goal, is to go toward isolation. We want x equals something. That's what we're looking for. So therefore, what we should do is take steps to get the x on one side, the numbers on the other side, because that's where we want to end up, right? So what I'm going to do is add 2x to both sides. You say, well, I don't know what x is, so I can't possibly know what 2x is. Right, but I know that if I add 2x to this side, and I've got a minus 2x, that'll give me 0. And the x's disappear from that side. Here I get 6 x's. And over there I've still got that minus 13. Okay, now that's looking like the ones we just did. Take care of this add or subtraction. Subtract 5. That goes out. 6x, see we're closer to isolated now. And over here, minus 13 take away 5 is a minus 18. And now just divide by 6. So that gives you x equals minus 3. So the idea of the 4 legal operations that we can use, we can add the same amount to both sides, subtract the same amount from both sides, and so forth. Well, I added the same amount to both sides. Even though I didn't know what that amount is, I added the same amount. So actually, I stuck to the rules here. It's just that that happened to be involved with x's. Let's do another one like that. And here's one of these things that hasn't been cleaned up. So now we're putting everything together. Now we're going to go back, get our techniques for simplification, and then we'll solve. Okay, on the left side, you do have some like terms. The like terms are the two numbers. On the right side, you got some other like terms. The terms with the two y's in them. So you simply add 6 to 3, that gives you 9, minus 8y. Here you got 1y plus 3y, that's like having 1 box of widgets and 3 boxes of widgets. You don't know what a widget is, but you got 4 boxes of widgets, right? So you add the two coefficients, that gives you 4y plus 6. All right, now let's get the y's on one side, the x's on the other. It doesn't matter which side you get them on. For example, I can add 8y here and 8y there. I have to add the same amount. So that goes out, there's a 9. This gives me 12 y's plus 6. And now the usual stuff, let's take care of the 6. 12y is equal to 3, and then divide by 12. Whatever is multiplying it, just divide by it. That gives you 1y, and this is 1/4. We wouldn't leave it as 3/12, that would, you know. Have to get the greater roll instead. All right, let's do one more. Let's do an equation now where we have to actually use the distributive law. Here we didn't have to do distributive law. All we did is combine like terms here on both sides. So let's throw in the kitchen sink here. 2 times y minus 6 plus 32 equals 8 minus 4y. Now I venture to say that if I ask for opinions right now as to what y makes that true, there would be dead silence. It's too complicated now. And that's a kind of a beginning equation in Algebra 1. You will see this again in pre-algebra and Algebra 1, but that comes right at the beginning of the course. That's considered very simple. And yet, we're past the point where our mind can look at it and get any sense of what y makes it true. Too much going on. Distributive laws, collecting like terms, you know, all that stuff has to be done before you even get some sense of what it is. And that's why you need a procedure. The procedure is actually more important than any particular problem. So let's bring in that distributive law. Let's bring in the 2. So this becomes a 2y minus 12. Now we've distributed, so we don't need parentheses anymore. So just add the 32. Nothing to do over here. This is as simple as it gets. But now we've got like terms here. So we add the minus 12 to the 32, and that gives us a 20. Okay, now let's get the y's together and so forth. I'll add 4y to this side and 4y to that side. Keeping everything in balance, that goes out. All you've got left is 8. Here you get 6 y's plus 20. And now to isolate that term, I'll subtract 20. 6y there. That goes out. So this becomes a minus 12. And divide by 6. And y is equal to a minus 2. So if you put minus 2 back in up there, it would work. The left and right sides would be the same. Let's try it. Minus 2 take away 6, that's a minus 8. Times 2 is a minus 16, right? Add a minus 16 to a plus 32 and you get 16. 8 minus 4 times minus 2. Well, 4 times minus 2 is minus 8. So 8 minus a minus 8 is 8 plus a plus 8. That's 16 also. It works. But that's not the kind of thing you can sit there and say, oh, well, I think it's 16. Or minus 2. Or, you know, I didn't hear anyone offering answers. So, see, the procedure is, actually the procedure that you've learned the past few days is extremely powerful. It's the only real procedure there is for solving equations. This is what's made algebra popular for hundreds of years. And you now know the secrets. And that's it. All right, let's do one more. Two x plus 3x plus 2 equals minus 4 times 3 minus x. This is just to keep our wits real sharp here about that distributive law stuff. The left side is not very complicated. Just add these two to get 5 x's. But over here we have to bring a minus 4 inside, and there's where the problem is, that when you're multiplying a minus 4 and you've got a subtraction, you have to be very careful. Your book stretches it out a little bit, and they say, well, make this minus 4 times 3 plus a negative x. In other words, they change subtraction to addition of the opposite. And that's so you can see how the signs work. Now let's bring the minus 4 in. Well, minus 4 times 3 is minus 12. And then add to that, because you're adding, a minus 4 times this. Okay, minus times a minus, plus. So it turns out to be a plus 12x, 4x rather. Plus 4x. All right, so the right-hand side looks like that, minus 12 plus 4x. Now, people generally remember this. This is a quick trick. They just remember, well, minus times minus is plus. That does work. Doesn't mean much, but it does work. It is a memory tool, so you won't make the mistake. And that second sign is always the problem. All right, now let's get the x's together. I'm going to subtract 4x from this side, and likewise subtract 4x from this side. Now it goes. This gives me only one x left. X plus 2 is equal to minus 12. And then isolate the x. X equals minus 14. Okay, let's do some homework. Tomorrow we're going to do the last section in the book, and I'll have your practice final for you to take home so that you won't be bored on Memorial Day weekend. Won't be. They told us, you know, keep them off the streets and don't let them get bored. Okay. This is, let's see, the section number is 1.5.
So there's no lab tomorrow?
There's no,
Is there lab tomorrow?
no lab, no.
Oh,
No, we have one more section we're going to do. No, we're done with everything but the final. And then, of course, we have Monday off, and then next week we'll be going over the final. And answering any other questions you have, by the way, any tests, any labs, you can bring them in.